Yes, it's there.
Okay, thank you. Okay, just to introduce myself, I'm Salvatore Calasso. I'm working in Lamborghini since 3 years at least. Actually, I'm responsible for the dimensional management in the R&D engineering department. Today, I'm going to show a short presentation related to the tolerance analysis model developed during my first activities. That was at the time of the trainship. It was the very first time that I used the a CAD tool as a CITO. So the presentation is organized in 2 steps at least. A first introduction of a very short, because my colleagues just saying in detail the approach, the model-based definition approach. Then we are going to see the case studies, 3 different case studies in particular. Then at the end of each case study, we will see the result of the tolerance analysis for each of them. Okay, as said before, the model-based definition, it's an innovative approach that is in developing in our world, because it's a very very convenient to use it in the design phase, but also in each phase that are involved in the developing of the parts. In particular, the strengthness of this method is that all the information are stored in a 3D CAD model, instead of producing different 2D drawings and to review the drawings each time we need to modify something. And so the strengthness of this method is that the same information that are important for the design phase are also the same information used for the manufacturing phase, for the measurement phase. But also it's very simple to understand the 3D model and to see it on a screen instead of 2D, to convert it into the view or sketch or sections. One important data that I was curious to note, that the 35% of engineering time is wasted in searching for redrawing the parts, and this is a no value at the time. Due to this method, the first data is that the 40% it produces a 40% or reduce in non-conformances due to inaccuracy in the drawing, at least a 50% in reduction in prototype build. So, which is the need for tolerance stack-up analysis? First of all, there are many reasons, but as you know, when you are dealing with a simple parts, maybe you are simple do a simple sketch using a 1D approach, for example, using a simple spreadsheet tool or model tool as analysis method. But the question is how to solve the problem when you're managed with such big engine, for example, or in general with a long stack-up assembly. So the reason to use to perform a tolerance analysis could be cost reduction to get a right reliability and performance of the part, but also to ensure the mountability of them. But in general, one of the key point is to increase the tolerance understanding, because everybody speak about tolerance value, but from experience, I noted that many times the value inserted in the drawing coming from experience. So the first added value in using a cut tool, or in general to have in using a robust approach in tolerance analysis, is the tolerance understanding. Here, just introduction of the different approach in the tolerance analysis. We can do we can do a simple 1D approach with for example with a spreadsheet, but the difference in using a cut tool of as a C tool, Six Sigma, is that we consider the entire 3D world. Sure, it's more is simple in considering also the geometrical tolerances apart for and the dimensional one, but which is the goal for the tolerance analysis. When we are dealing with the assembly, sure, we have a cost related to a single part. But for from the engineering point of view, we should have the tighter tolerances as we can, because this approach is very safety, let me say. But the reality is that closed tolerances means also more expensive. So the goal for the assembly is sure to have a minimum cost for acceptable performance for the entire assembly. And here, briefly, we can approach the problem into a way. First of all, the worst case, for sure, that's answer 100% of success, or we can speak about statistical approach. That is from my point of view, the real approach, because the possibility to have get the worst case is very short, in particular if we are dealing to long tolerance stack-up. In the next slide, we are going to see the three case analyzed. In particular, they are divided in three different goals. The first one is the gap between the crankshaft shoulder and the shoulder related to the engine block. And this the goal of this example is the cost reduction. The second one is the check the valve spring length variability in order to allow the right performances, but also to get the right reliability of the component itself. The third one is for example, a water pipe mountability, in which our goal is to ensure the mountability of the part, in particular between the screw and the two parts between, so the pipes and the block itself. So starting from the first one, our goal is to have a gap between the two shoulders, highlighted here on the right, between the shoulder of the crankshaft and the shoulder of the block. In particular, the gap should be measured or equal than 1 millimeter. The approach is used is 3D statistical approach using CTOL, and considering a capability, process capability of 1.33 as assumption, because at the start, the first problem, when we start analysis, the tolerance analysis, is that we didn't have the right capability or the right statistical distribution of single part or single tolerances that enters in the tolerance stack-up. But for our internal standard, our supplier should guarantee a minimum standard, a minimum capability standard of 1.33 as a CPK. So for our point of view, it was a good starting point. The first question for that case was, which is the critical gap? Is there a gap that here is more critical than the other? So simply modeling the case due to the CTOL model, we rapidly understand that, for example, the shoulder related to the third crank shoulder was the critical one. Our goal in that case is to focus on the block part, so on the block machining, because it's from us it's the complex part for the engine. So we focused on this value that was tolerated in plus minus 0.03 millimeter. And our goal is to understand which is the maximum value that we can accept, keeping the goal to have at least 1 millimeter of the gap between the two shoulders. So starting from a worst case approach, we didn't increase this value at plus minus 0.1 millimeter. But using a statistical approach, we sure did it, because our limits was the black line, let me say, and the statistical limits of the process, of the entire process, are highlighted by the green flag. So sure, we can pass through plus minus 0.1 millimeter, but also plus minus 0.2 millimeter is good, but also 0.3 millimeter are good for our application. At the end, we choose on the plus minus 0.2 millimeter for the shoulder related to the block, because we for safety reason, but also to keep a margin to work on the other part in the future. So we modify the value coming from plus minus 0.03 millimeter to plus minus 0.2 millimeter. So finally, the result was a tolerance growth plus 500 66%. That in terms, we estimate a reduction, a cost reduction of €3 for engine. That could be a very small cost reduction, but it was just an example, because in that case we modified just one tolerance value. Based on the 2019 sales data, it means €3,300 of saved. The second case it was related to the valve spring length. Our goal is to understand which was the length variability, because our goal is to understand the impact of the length variation on the component itself, because changing the length in installation of the valve spring means also modify the stresses on the components themselves. So the case was developed for the intake side and for the exhaust side. We organized the entire tolerance stack-up, and considering the most impacted in terms of volume contribution, we understand that the valve cutter was the most critical components, because the dimension that entered in the tolerance stack-up was the 1.5 plus minus 0.35 millimeter. So first step, we understand which is the most impacted tolerance in the tolerance stack-up. Then the second step is to understand together with the supplier which is the reason of this value. And we discovered that our supplier had the possibility to reduce these values, and the reason to have the plus minus 0.35 millimeter on the drawing is that its capability can change along the time. So it has the possibility to have a very tight tolerance variation, but we should introduce a check to the different batch in the time. But this was a good indication for us, because we understand that we could consider installation length variation in plus minus 0.35 millimeter for the intake side, and in plus minus 0.30 millimeter for the exhaust side. The last case, the third one, was the water pipe installation. Our goal is to answer the mountability of the pipe. Here we starting from a original drawing that not followed the actual ISO standard, and simply introducing a new regulation and simply modeling the cases due to CETL, we were able to answer the mountability of the part, increasing the tolerance and the drawing, so also reducing the cost. On the left, we have the original cases, and as you know, the R2 screw was not okay in terms of mountability, because this 2.7 in sigma means 7 over 1,000 defects. So each 1,000 engine could be a probability to have 7 failure. we modify the drawing, increasing the tolerances, but changing the tolerance scheme in order to shorten the tolerance, the tolerance stack up. And the result was that the tolerance position on the cylinder block side passed from plus minus 0.1 millimeter that was indicated as dimensional tolerances and not as geometrical position tolerances. So start from plus minus 0.1 millimeter to 0.2 millimeter as position tolerances. For the water pipe, we pass from 0.1 millimeter to 0.2 millimeter using the maximum material modificator, and with this value, we ensure the entire mountability of the part. So the goal was the cost reduction, the reliability and performances, and the answer of the mountability. This due to this method, we were able to analyze the three cases. And now I want to show a result of using this method on our product. Okay, maybe the last slide is just a suggestion. So at the start we speak about the misinformation at the start of the analysis, because usually when we start the analysis we didn't have the right statistical distribution of the single tolerances. So when you are in during the design phase, the developing phase, we can use the methodological result in order to substitute the real distribution to the standard one, and to repeat the analysis and to recheck it. And this could be sure more robust in terms of final results. The presentation is ended. If there are some questions, I'm very curious to answer to them.
I see a question in the chat from Matteo. Do you want me to read it to you?
Yeah, okay. We can